Alright guys, welcome to adding, subtracting, and multiplying complex numbers. So the essential understanding we're going to look at today is how we can perform operations on complex numbers. Okay, division's not included in this because we do need an extra piece, something that's called a conjugate, to help us simplify complex numbers. So again, essential understanding, how can we perform operations on complex numbers? So what is a complex number and when does it arise? So I want you to consider these two equations, both simple, and we have x squared minus 1 equals 0. So let's go ahead and solve for x, and I do that here by bringing the 1 over and then square rooting each side. So we get x equals plus or minus 1, real number solutions. However, if I look at my second equation, I have x squared plus 1 equals 0. Subtract x and take the square root of both sides. Now I'm left with x equals the square root of plus or minus the square root of negative 1. So I think to myself, well, there's no number I can do to get negative 1 under a radical. So in Algebra 1 you learned, well, you can't take the square root of a negative number. That's not necessarily the case, okay? And it deals with this idea of what a complex number is. So on the next slide I show you the graphs. Okay, let's look at these two graphs of these equations. Okay, and it'll give us some idea of when a complex number or imaginary numbers will pop up. So here's the graph of x squared minus 1 on the left. Notice how we have negative 1 and 1 are zeros, or the roots. Those were the solutions to the equation that I solved by hand. Now if I look at x squared plus 1, okay, I notice that my graph does not cross the x-axis. Okay, so there are going to be no real roots to this. There is no real solution to this because this graph does not cross the x-axis. So the idea, oh hey John, the idea here is that complex numbers arise when we try to solve quadratic equations. Okay, and those quadratic equations that don't cross the x-axis are typically equations or functions that do not have real solutions. They'll have complex solutions. So complex numbers arise so that we can solve these quadratic equations, so we can solve all quadratic equations. Okay? So on the next slide here, there's some important things. We use I to represent imaginary numbers. I is the imaginary unit, imaginary part. We use I, like I said before, to solve all quadratic equations, including numbers that are negative under that square root sign. So I is used to represent the square root of negative 1. Okay? This also implies that if I square both sides using some algebra, I get I squared is equal to negative 1. Both those are very important. So now when we look at a negative number under the radical, the square root of negative 2, we can simplify that. We could have simplified it before, but now we can account for that negative 1. So I simplify, I have square root of 2 times negative 1, and then I break apart that radical. Square root of 2 times the square root of negative 1. Square root of 2 stays the same, but now I interchange, I substitute root negative 1 with I. So I just rewrite this. I have square root of 2 times I. That's the same thing as I root 2. You put that imaginary number, imaginary part first. Okay, so now this is when we can define complex numbers. All of a sudden I've told you what I is able to represent. A complex number is in the form of A plus BI. That's your complex number. A and B are elements of the real numbers, and BI is called the imaginary part. So when we look at the number system, we dealt with real numbers and we thought that was the largest number set. But in fact, complex numbers is even larger than the real numbers. So the complex number set here, and if you notice to the left, we have real numbers. The complex numbers, A plus BI, is the largest number set. The real numbers all fall into complex numbers. Real numbers can be written as A plus BI, where B is equal to 0. So you have 0, negative 5, 1, 7 through 2. I could throw on a 0i here, or a 0i here, and that all of a sudden makes them a complex number. Okay? But we don't have to write 0i. If you look to the right, you have imaginary numbers, A plus BI, where B doesn't equal 0. So notice we have 3 minus 4i, 7 plus I root 3. Okay? So imaginary numbers are still in that same form, A plus BI, where B is not 0. Okay, And then we have pure imaginary numbers when your a value is 0. So like 5i minus 3i, those are pure imaginary numbers because there is no real part. Okay? So the big difference here between real numbers and imaginary numbers is that b is 0. There is no imaginary part. It's 0. So real numbers are not imaginary, just like imaginary numbers are not real because of this fact. b is equal to 0. We do not have to write that part, so we can erase that and just leave our square root 2, -5, and so on. So how do we add, subtract, or multiply these complex numbers? Well, if you can combine like terms, then you can add and subtract complex numbers. So in the first example here, I have 8 plus 3i, and you're adding to that 7 plus 5i. And here, we're just going to combine like terms. And when we combine like terms, we're looking at the real part. So if you look in blue, a is a real number, a is a real number here, and this is a real number. Group them together. Your imaginary parts are also grouped together, and then you combine like terms. You get 15 plus 8i. Okay? Very similar to like if you had 8 plus 3x plus 7 plus 3x. Combine your x terms, combine your constants. In part B, it's subtraction. Can be done very similarly. I can't say that. You're going to take the 8 and 7 and put them together. 3i and 5i go together. And notice in between is subtraction. Okay, but on the outside there it's addition. So there's a difference there. I kept the addition, but I put minus inside. You could also distribute the negative through first. Either way is fine. 8 minus 7 is 1. 3 minus 5 is -2. 1 plus -2i is the same as 1 minus 2i. So either answer is acceptable. So again, adding complex numbers, match up the real parts and the imaginary parts and add them together. It's really just similar to combining like terms. Multiplication is a little more tricky, but it's similar to real numbers. And when we multiply these first two examples here, those are binomials, 2 terms and 2 terms. So you can apply FOIL, which only works for a binomial times a binomial. You can use the distributive property, which is what FOIL is, or you can use something like the box method. I chose just to distribute, and my way to distribute here is I just take each term of the first binomial and multiply it to every term in the second. So that's where you see the 5 times 9, 5 times 8i, 3i times 9, 3i times 8i, all here. Okay, now the difference between adding and multiplying complex numbers, I can multiply 5 times 8i. That gives me 40i. Okay, 5 times 9 is 45, 5 times 8i is 40i, 3i times 9 is 27i, and 3i times 8i is 24i squared. And I had that circled, okay, because that's where you're going to need I squared is equal to -1 here, and when we get into our other example, right down here. I squared is -1, so replace that. 24 times -1 is -24, so there's where that -24 comes in. I've multiplied all my terms now, and so what I'll do is just combine like terms. 45 minus 24 is 21, and then we have 67i. Now, 8 plus 12i times 4 minus 2i, again, combine like terms. So distribute or FOIL, and there's my 4 terms. 8 times 4, 8 times minus 2i, 12i times 4, 12i times that minus 2i. Again, the 24 minus 24i squared, that becomes positive 24i squared, okay, which becomes, minus 24 becomes minus 24 times -1, which is positive 24, okay, and that's where we get the 56. 32 and 24 make 56. Okay, so that's combining, adding, subtracting, and multiplying complex numbers. In the next video, you'll see how to use complex numbers and conjugates to simplify when you're dividing a complex number. So if you have any questions or comments, you can type them below or email me at nicholas.bennett@dc.gov.